Thank you. And let's discuss the first question. The first question is a monotonic array. Array given, and we have to decide if the array is a monotonic array. The definition of a monotonic array is either it's an increasing array or decreasing array. Yeah. Let me go to the example. Like the array is 1, 2, 3, 1, 2, 2, 3. And as we can see, it's a non-decreasing array here. For this situation, it's a monotonic array. Monotonic array here. Yeah. And there is another example. It's 6, 5, 4, 4. It's a non-increasing array. For this situation, it's also the monotonic array here. And another example is example 3. The array has 1, 3. We can see 1, 2, 3 is it's an increase. It's an increase, and 3 to 2 it's a decreasing. So this array has an increasing and a decreasing subarray, so it's not the monotonic array. So we have to return false for this example. Yeah. And then another example, example 4 is 1, 2, 4, 5. It's increasing, only increasing. Yeah. It's also monotonic array. And the last example is 1, 1, 1. It's interesting because it's you can say it's a non-decreasing or it's non-increasing. In this situation, it's a monotonic array. Yeah. Is it clear for the question?
Yes.
Yeah. So do you have any idea how to solve this problem? Let me let me try my approach.
So I think either it should be increasing or decreasing.
Yeah.
So if it is increasing, it should keep on increasing. If it is decreasing, if there's a mismatch, and then we can return false.
Yes. It's two different situations. One is non-decreasing, and another one is non-increasing. Yeah.
So if I start with like, if I see 0 and 1, if 0 and if 1 is less than 0th index, that means it should be decreasing. And if 1 is greater than 0, it's increasing. After that, all the elements should follow the same sequence.
It's not sure because after that maybe they have like some situation the current index will be equal with previous index, right? So that means we need to skip that situation. So if
Yeah,
yeah,
till we find a, a position where we can decide, and then we can keep on going forward.
yeah, but if the current index value will be equal with the previous index value in that situation, we should skip that one and we don't compare that one.
Yes.
Yep.
Yeah. Oh, I lost my internet connection. Yeah, for a few minutes. So, what you said is compare the first two elements to decide if the array is non decreasing or non-increasing, and iterate the rest of the array and find the contradiction. If find the contradiction, it will return false.
Yeah, we can even iterate the entire array and keep on finding like.
Yes. Yeah. Mm-hmm. Yeah, that means find the first two elements, compare the first element, and then
If
Yeah.
we compare the first two elements, it doesn't correct because the first two element could be equal. If the first two element will be equal, so we don't know that one will be increase or decrease.
Yeah, like the example 5. What if it's 1, 1, 3? Yeah, 2.
We should
1, 1, 3.
find like the first when we travel from left to right, we should find the couple. Make sure the first couple, the value should not be equal, and then we compare. And
Okay.
then after that of the element, and if it's not equal, it should follow that.
Find the non-equal elements to decide it's increasing or
The first one, the first non-equal element.
The first one non-equal. Yeah, first one non-equal element. Yeah. Yeah. My idea is to compare the first element with the last element.
Yeah, it's also work.
Yeah, it's also work. It's
the same. You don't know.
Yes, you don't know that one will be because of all of the elements should be equal. Yeah.
Like the example 1, 1, 1 here. Yeah. Even the first two element and the last element, they are equal. Yeah. But we can try. Yeah, we can just if it's equal, it's non or increasing, and iterate the other element in that array. And
But your way can work. Your way can work if you compare the first element and the last element in the array, and if it equal, and then if you travel through the position 1 until position n minus 1, if they have the value different, that means you need to make sure that every value in that array should be equal, right? If they have the value different with the first element and last element, you know that's one you will return false.
Yes, yeah. Yeah, in this situation, if I found the first one equals the last element, and then I compare the rest of the array, if the rest of array element is not 1, it will return false. Yeah. So, yeah, it's like the approach is going this way, and maybe I'll show my implementation. Yeah, I have the like a flag. Its default is increase. Yeah, if the first element is less than the last element, the flag boolean is true. That means it's increase. Else it's false. And then I iterate the whole array and find the contradiction. If I find the contradiction, I return false. If not, at last I return true. Yeah. Any question? Because it's only two possibility here. One is the array is non-decreasing, and another one is non-increasing.
Could you scroll back to your code?
Okay. Yeah. I include some corner cases, like the array is just one element. In that situation, it's always return true. And then I have a boolean here. This boolean is like an assumption of the array. It's increasing or decreasing by compare the first element and the last element.
So where would you treat the equal element if the first and the last are equal? You can make the increment equal for?
If it's equal, I just have the flag to be false. And then I iterate the whole array and find if I had some.
It not make sense because I think that he say correct. I think that if that one will be equal, you cannot make sure like the increase will be false. Oh no, yeah, the increase will be.
Yeah, it's I can just pick one of the possibility and to find the contradiction. If I find it's false, if not, so my assumption is reasonable.
Right. Yeah.
Have any question? Could I move to the next question?
Why you are doing this AND operation like increment, or you are taking? You're considering if both are true, then only in that case, in the line number 11.
Line 11, yeah.
Yeah, this AND operation, right?
Oh, I have.
This is an AND, yeah.
I think let me tell like this. For example, you have AI greater than AI plus 1, right?
Okay.
AI, yeah, AI, yeah.
Greater than AI plus 1, and it will increase. That means, yes, that means, so I only want to get a test case. For example, if the A0 equal with the A minus 1, so you say that one is not increase, so increase equal false. And now you have an AI greater than AI plus 1. So that means exists the number in the middle of the array different with the first array and last array, and you return false. That's incorrect.
Yeah, she only look for the contradiction.
Yeah.
If it's equal, then they just like ignore whatever you look.
Yeah, the line 11 is that if I assume the array is increased, but I find it's a decrease 1, then I return false. The line 12 is I assume the array is a decrease array, but I find an increase element in my arrays. So it's a contradiction, so I return false.
No, got it.
There's can I just say there's another way of thinking
Mhm.
I mean, at least the way I went for. It
Mhm.
was having two booleans, increasing, decreasing,
Mhm.
and having like 2 pointers right next to each other in the array, like iterating next to each other,
Mhm.
and then just if the previous is less than the next one, then I set increase to true. If the previous is greater than the next one, then I set decreasing to true, and I compare if both of them are true, then it's false. Otherwise, return true.
Oh, yeah, 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 yeah.
Yeah, that one is very
Mhm.
good solution. I think.
Yes, yeah. That means you can move the two pointer and find the boolean if also true or also false. That's return false.
Yeah.
Yeah, because you only can have one of them to be true. Yeah.
Yeah.
Mhm. Yeah. So could I move to the next question?
Yeah.
Yeah. This is a second question. Next greater node in linked list. We are given a linked list with head. The head is the first node of the linked list. And in this list, we have the node 1, node 2, node 3, and each node have a next larger value. For the 1, maybe it's 2, and the node 2, the value is 1. The node 3, the value is 5. So for the first node, node 2, the next larger node is 5, because 1 is less than 2, but the 5 are larger than 2. So we return the next larger node value here. And for the node 2, it has a value of 1. The next larger node is 5. So we return the 5 here. For the last node, the node value is 5. We can see it's already the last node. So there is no node on its right. So we return 0. That means there is no node larger than 5. Yeah. So the we can look at another example. The node the list has 5 nodes. The one is 2. We can see the next larger node than 2 is 7. So we return the 7. And for the second node 7, there is no node larger than 7 here, so we return 0. For the third node 4, there is the 5 is a larger node, so we return 5. For the node 3, we also can find the 5 is larger than 3, we 5. For the last node, there is no node larger than 5, we return 0. Is it clear? Yeah. What's the question? The question is to return the next node larger than current node and return the value. If you didn't find that value, just return 0. Yeah, we can have another example here. We have a linked list, have 8 element. 17519251. And now we will find the next larger node. For the next larger node is 7. For 7, it's already the maximum value in my linked list. So I didn't find any node larger than it. So I return 0. For 5, 9. Oh, there is a 9. Sorry. Yeah. For 7, we find the 9 is larger than 7. So I return 9 here. For 5, the 9 is larger than 5. And I return 9 here. For 1, also we can find the next larger node 9. For 9, it's a maximum value here, so I didn't find any node larger than 9, so I return 0. And for 2, I return 5. For 5, there is no node larger than 5. For 1, there is no larger node for 1. So I return the array. This array, each element is the next larger node for the current node. Is it clear for this question?
Yeah.
Yeah.
In this question, it's very similar to another question we also discussed in SD skill, lead code practice.
Yeah, so I think we did some similar questions before.
Yes.
Where we'll take something like a stack approach.
Yes.
And we'll put first 1, and then we'll have 7. We'll keep on removing things which are smaller than 7. 1 will go away, and 1 next larger is 7.
Yeah.
And then we'll put 7 in the stack.
It's the stack is it's a decreasing stack. Yeah, that means in that stack, 1 we find a new element. The new element is greater than the stack top. We will do pop. We will do the update the RES, the result return, and then pop it out. Yeah. Let me try an example here.
So what do we keep on the stack?
Yes.
The decreasing elements.
Yeah, because we need the next greater node here. For example,
that's a value, right? But what actually we keep on the stack?
We should keep a class. In that class, have a both variable. One is index, one is the value.
But this is a list. We don't want. If we keep the index, that means we have to traverse.
Yes.
We can create a class.
Yeah, it's a good question. Yeah, because it's a linked list. There is no index for the linked list. So no. My approach is transform the linked list to array.
No, actually, you doesn't need to do that. You only need to have a one variable. Every time you travel through the linked list one by one, you will increase the index by you have a one variable like I or something.
Max so far. You can take a variable like max so far, and each time iterating, you just update that.
But then when you have to look back, and then when you pop it out from the stack, you have to update that node, right? Then you need to know where that node is.
Maybe have 2 pointers. One pointer is pointer to the current node, and the next pointer is to find the next greater node.
What if we keep the address of the node on the stack?
I know we doesn't need to do. I have the idea we can, because we can have a stack of the integer array, right? The integer array have a maximum 2 element. First one will be the value, second one will be the index. So that means we doesn't need to create a new class. We can have a like the integer array of the 2 element.
Yeah, I think either we have to use the 2 array or we have to put some sort of pair of the element and the index itself in the stack.
Why can't we put the address of the node on the stack? The address should be an integer only, right?
But
still you have to put the index along with the address.
But the return is a vector, so how will you get the index for that element in the vector?
Yeah, but that return will be different. We don't count the return in the space complexity, wouldn't that?
Yeah. Anyone want to share this approach? Yeah. Keep the linked list data structure. Yeah. Because my approach is transform the linked list to array and solve it in the array. Yeah. Maybe.
But this is, I think, language dependent. If we go in Python, we directly put the element node itself inside it. In C++, might be some. So it's a bit of more language agnostic, I think.
Oh, so we need the position where to give it in the answer. So if I keep the address or something, how will know what position it was originally?
Yeah, so along with the address, he'll have to again put the index also.
Yeah, the position. Yeah. So if I'm traversing my linked list from, if I'm at the, if my current is at 0, so I have to tell like, okay, this node was at 0th position. Then only I can put back in my result array.
I'm thinking if I put the address, I can modify the existing linked list to contain the result. Because if let's say when I pop it out, I know the address of that node. I just go ahead and update that.
Where you will update? You can't mod until you add a new property in that node. How you will update that node?
I know the address of the node. That means I have a pointer to that node, right?
Yes.
Then I can modify the value of that node.
If you modify the value of that node, that means you are modifying the input.
And you'll lose the information in that case.
I mean,
that's right. That I try to I reduce the value of the. I mean, I reduce that linked list to store the information. But there's always a pro and con in there.
Your idea is like using the pointer only, do some modification, but it will modify the actual input.
Yeah, or you have to trade with the time. So in that case, if you keep just the pointer, then you will have to enumerate the list again to get the index.
Yeah, yes. You need an index for the output at any cost. Yeah.
Yeah. So, for the index of the output, we can have a count. If I iterate the linked list forward one step, I increase the count. That count is the index of the node. We can do that. Yeah, to keep track of the index of the node. Each time like the current is a node linked list. If I do the current move forward one way, I just increase the count, and that's the current pointer. I use another pointer to find the node greater than the current node. Yeah, is this your approach or something else?
Yeah, I think it's good, yeah.
But in this approach, the time complexity will be all of n square, because you use a 2-pointer, and for each element you have to iterate the whole rest of the array to find the next greater node, and then you move this pointer forward and look for the next greater node here. Yeah, is that possible?
Yeah, it's both.
Mm.
It's possible, but we don't want to follow that solution.
Yeah, if you have a different idea, you can share your idea.
No, I agree with the idea using the stack.
Yeah, if you transform the linked list to the array, and we can do it in all over n. Yeah, because
But either way, we'll have to use a stack because it's a monotonic stack, right? So you will have to use a stack. That is what I think. If either you use a pair, whatever we said earlier, or you use your way of converting it into an array, and you still use the monotonic stack to find the next greater element.
Yes, that's correct.
Oh.
Yes.
How to use the pair? You mean what's the?
Because the pair, because if I don't know in the C++, but in the Java, if we have only the integer that is the primitive type, we cannot put in the stack. But if we have an integer array, that's one is like reference type like the memory types or something. We can say we can add that one into the stack. So that means the integer array, that means we have the bare 2 element, first element will be index, second element value like you show. And then every time we add into the stack, we create a new memory for the index and the value, and we add into the stack.
Yeah, that's correct. Yeah. There's a similar way to be implemented in a C++ also. So you have a stack which has a pair, as you said, like, pair will be pointing, first will be pointing to the index, and second will be pointing to the value.
Yeah.
Okay. The pair, the first element of the pair is
int. Both are int. Yeah. Index, and the other is the value.
Oh yeah. Okay. Yeah.
Yeah, it's up to you. I mean, whether you want to put in the first as index or in the second.
Right. Either of it works.
Yeah. In this way, I needn't have another array to store. I just store the linked node to the stack, because the pair also already has the index and the value information. Yeah. In the stack.
Yeah, but still you need to have a vector for an output, right? So you have to have a vector output. So either way you have to have a vector.
Yeah. Could I show my approach? Yeah. Sure. This is my approach. Yeah. The result is my output vector, but beside of this vector, I have another vector array to store each element value in that array, and the rest of it is like just use a stack to find the next larger element. Yeah.
So this is the monotonic stack, right? That is the way one actually gets the next greater node.
Yes, this is a monotonic stack here.
So you keep on popping out all the elements in a stack if they are lesser than the top value of the stack, right?
Yes.
For the element.
I put the index in the stack.
Right.
So I can keep track of the output result. Yeah. The stack top is the index. Which index I could output my array I element here.
Yes, yes, that's correct.
So if you want, actually, I can quickly show you the way the stack pair is implemented. I can quickly.
Yeah, sure.
Okay.
I stop share.
Okay. Okay, can you see my screen?
Yes.
Okay, so it's almost similar the way you are doing it. So this is the stack and this is the pair of intent. Okay, I start with the current. This is the least node, which I just pointed to the header. And then this is the index, what you are talking about, the counter. And this is my output array. Okay, so every time I go in a loop, I first add one element to that output array. And then this is the whole stack, the monotonic stack approach. I just compare the second element of the stack, that is what the value is, no, with the current value. And then I put that in this output array. Okay, I keep on popping and put that in that output array. And then I push that in the stack again. And then increment the counter again here and then move the next node in the linked list. Okay, it's almost the same what you did.
Yeah, but you save the space complexity. Yeah.
No, just one small array vector, right? That's all.
Yes. Yeah. You didn't use extra vector.
Yeah. One.
Good.
The stack could be in this case, stack will be similar to the vector, because like in the worst case, the size of the stack will be the same as the size of the linked list, right?
No, it's not. It doesn't.
Because in the worst case, it's gonna be
correct.
like decrease. The whole array gonna be in decreased order.
Yeah. That's correct.
But that is the way you can actually get this, right? So you need to use a stack for that monotonic stack approach. So either way, if you go both the solutions, it is going to have the same effect.
Yeah. So I don't see this one is saving a space than the previous solution.
Oh yeah, you mean to say the space? It's not a big
thinking.
thing. Yeah, exactly. It is almost the same, but as she said that instead of converting the linked list into an array first, and therefore she used the array earlier. So that's the only thing which is not there.
Yeah, I mean, it does not save the space, but and interior will be okay with both the solution. But I think if someone go with that, that's a smart solution in terms of maintainability of the code. So if interviewer is looking from that point, so they will give you a plus for that.
Okay.
That's my take here.
Yeah, maybe it all depends on them. Yeah, that's true.
Yeah, this approach is more directly to the question because it keeps the linked list data structure. Yeah, and to deal with the stack. Yeah.
Yeah, it's okay. So yeah. I'll just stop the sharing and you can continue the next one.
Okay.
Okay. Thank you.
Yeah. Any question for this problem? If not, we'll go to the last question. Yes. It's a 42 game. We have a 4 card. Each card contains just one digit number from 1 to 9. And we need to judge whether they could operate through times divided and minus parentheses to get the value of 22. If we could use that operators to get the value of 22, then return true.
24, yeah.
Oh, 24, yeah, 24. If not, return false. Yeah. I'll go to example 2, example 1. The input is 4187. And when we put the 8 minus 4 together and times the difference between the 7 and 1, the answer is 8 minus 4 is 4, and 7 minus 1 is 6, and 4 times 6 equals 24. So in this situation, we can get the 24, so we return true. And another example, it's 1212 is given. And for this situation, we cannot use the operators to get the 24. So we return false here. There are some notes here. The division operator represents real division, not integer division. For example, 4 divided by parentheses 1 minus 2 divided by 3. So the 2 divided by 3 is about 0.67, and 1 minus 0.67 is about 0.33, and 4 divided by 0.33 is return 12. If it's did integer division, the 2 divided by 3 will be 0. So the whole calculation will be 4. So this notice mentioned the division is real division. It's not an integer division. And another one is every operation done is between 2 numbers. We cannot use the minus as a unary operator. For example, with the 1111 array as input, the expression minus 1, minus 1, minus 1, minus 1 not allowed. Yeah, that means the minus operator is only used for the operator. It cannot be a minus 1. Yeah, it only can do 1 minus 1 minus 1 minus 1. Yeah, you cannot put the minus operator behind some number and treat it as a negative number. And the third is you cannot concatenate numbers together. For example, if the input is 1, 2, 1, 2, you cannot write as 12 plus 12. That means the 4 card is separately. You cannot put 2 cards together to look at the one number. Is it clear for this question? The 24 game.
Yeah.
So for this question, I implemented, but I have no idea for the detail. I just think about the 4 digits are given. Maybe I can choose some of it to get some result and put that result together to try the 24 output. I just think it's it might use a DFS, but there is too many details to deal with, like how to put the parentheses together, how to choose how to deal with the denominator is 0. Like if it's a 4, 4, 7, what if the 4 minus 4 is 0? But we cannot do 8 divided by 0. So anyone has any idea?
So you're
I think-
saying it's a DFS. So like,
Yeah.
why do you want to go the, I'm not saying you should not, but how it came to your mind, like we should be using a DFS? It's because, you know, you take all the 4 inputs and do all the operations, you know. So if you try to do all the permutations of each and every operation, it turns out to be a very big list, right? So
Yes,
a
yeah.
maximum, what it says in that solution is like it can be around somewhere like 9,000 some possibilities. So that's also still not a big thing. You can make them as a list and then actually resolve it. You know? So instead of that, you are trying to say that you can use the same, but if you do a DFS approach, it handles all these things on its own. So the code becomes more easier to implement, right?
Yeah, for the DFS, maybe we can do some pruning to to decrease the complexity of the, because for the DFS, it's only 4 number in the array, so the combination is not too large.
Okay, but when you say about the braces, right? How do you take care of the braces?
Yeah, that's a
Oh, sorry, brackets, right? Yeah.
Yeah, brackets. Yeah. So anyone has any idea?
What if we do the BFS?
BFS.
Can we do that? It seems like it. We
So,
can
you know,
find a shortest path, and we have the destination, right? 24, and the target. Probably, yeah. I don't know. Yeah. The first level, I think it would be, in this case, example 1, would be 4 plus 1, 4 plus 8, 4 plus 7, right? And then do the 4 times 1, 4 times 8. But I don't know if that would be efficient or feasible.
Yeah, in BFS, what I think, you will have to store every time whenever you complete a level, you will have to store all those values and then compare. But in DFS, you can always compare, immediately get the result and compare with just one value, 24, right? So maybe in that case, DFS is slightly easier.
Is it possible to actually draw one case? Or is it tree?
Okay. Yes, I agree. It's a tree. 4, 1, 8, 7. And the first try, we can do the 4 plus 1. Yeah. And keep the 8, 7 here. And another way is to do the 4 minus 1. Do the 4 times 1. 4 divided to 1. Yeah. Is that the tree you meant to show?
Yeah, I think then you can actually go and add 4 plus 1. No, in the below one, you know, because when you go to the next level, for 4 plus 1, it will be 5, right? And then 5 plus 8, and then you again go with the tree. 5 plus 8, and then a 7, yeah. And then again, in this, the same will be 5 minus 8, 7, yeah.
Yeah, minus 8 and 7.
And then you will have to make that multiplication, yeah.
Yes. That's the DFS, I think.
Yeah. So this way, Then you go for the third level again, and then you will make 5, 8, 7. Yeah.
7. Yeah. And for this one, we can get the 3.
Yeah. Let's focus on only on the first one, because the others will repeat, right? Yeah.
Yes.
So you go to the third level, it will be 13.
It's a 13.
7.
13 minus.
No, it won't be 13. Yeah, it will be minus 3.
Oh, that's mine. Yeah.
Oh, yeah, 13 minus
13.
7.
Yeah.
Sorry,
13 minus. Yeah.
My bad. Yeah.
13 minus 7.
13 into 7. 13 divided by
7. Yeah.
And then you get the results here, and then you equate that with 24, right? Yeah.
20, and it's a 6. It's a 91, and it's a 2 point. No, not 2 point. 1.8 also maybe. Yeah.
How do we handle the division, like it real division, not the integer division?
My approach is to transfer the integer array to the double array. That I treat it like the 4.1 and 1.0 and 8.0 and 7.0. When we do the divide, it will return the double instead of the integer division. Like if I do the divide between two integers, it will return 0, but we did the division between two double, it will return 0.33 like that. Yeah, that's in C++. I often to transform the denominator or nominator to the double. So the division will be the real division, not the integer division. Yeah.
So this is kind of backtracking approach only, right?
Yes. Yeah.
Like you'll go through the entire length of that. If you find, I mean, if it gives you the result well and good, else you'll go for the next one, right?
Yes.
Yes.
Yeah. And we're looking for the 24. Once we find the result is 24, we return true. If I iterate the whole tree that didn't find the 24, then return false.
So it's like
so
for every backtracking, we must use DFS only, because the length will be shorter and length will be shorter in this case compared to that of the width. So we shouldn't use BFS, right? Whenever we have backtracking problem, can we draw some conclusion like that?
I think, yeah, what you say makes sense.
Yeah, because if we have width will increase, then BFS, applying BFS will be a bit more, computationally it will be expensive, and length will be, yeah. So
can you say it again? Can you say it again?
In the backtracking problem, see what will happen for corresponding to each one. If you see 4, we are getting gradually at every step the width will start increasing.
So your plan is to use a BFS.
Yeah, in first step we have 4 nodes. Let's take, four those things. Now each will expand to another 4. So it will be like 4 into 4, 16 you'll have in the second stage. Third stage 16 into 4. Subsequently the width will start increasing, but the length will be minimal only. It will be shorter compared to that of the width. So it would be better to use BFS in case of backtracking.
Oh yeah. Yeah, I know what you see. It's like the first level we get this 4, and the next level we just we will keep track of the next level. Like we get the 3 plus 8 and 7. And 3 minus 8, 7.
Yeah.
And we did the search layer by layer, not the backtracking way to find the 24. So layer by layer on each layer. But for this, I have to do the whole calculation.
Yeah.
Because in the first layer, I just do the calculation of the 2 number. I left 2 number unused, and the second level I use the 3 number, and only I go to the last layer. At that layer, I can get the output.
One more thing here, when you are saying that you're using, in the first layer, you are using 2 inputs. So you are taking care of the brackets also here, right?
Yes.
So yeah, so you don't have to explicitly use a bracket as an operator. That's right. Because in the second one, when you are adding 5 to 8, so you are using 3 elements in a bracket. Okay.
Yes.
And I think the other gentleman who was saying about the DFS, so we are doing a DFS way, but he was saying the same thing what you are trying to show. It keeps on increasing in the each level. The number of elements, they go on increasing, and it becomes very cumbersome to actually keep track of it and do all the calculations, right?
Yeah, exactly.
Yeah, but let me think for the BFS. If we think about BFS, then at the last level, we will see, you know, what node is 24, right? So there could be many paths that don't take to 24.
But
right?
in the case, if we get a 24, we hit the 24 very early, so we don't have to do all that stuff.
But
that's the only thing he was trying to mention, I think.
No, but I'm thinking that, you know, if we look at the last level, we see it 24, and then I'm thinking now, what if we invert the tree and to see, you know, we start from 24, and with that given number, can we is there a path to get 24. There?
And now I have the
like kind of trace it back to see if we can.
And we back. That means that the 24 minus 4, 24 plus 4, and 24 times 4, 24 divided by 4. And our goal is to get the 0 by using all of this number. Is that correct?
Yes, I don't know if it worked, but you know, I was thinking, you know, we might, if we go, you know, bottom up, you know, so instead of explore all the, you know, path, then we, you know, maybe if we go bottom up, it would be faster.
This is DFS. What I'm thinking is for the DFS or BFS, we miss some situation. Like in the DFS, we only consider the first 2 elements, put them together. What if it's 4, 1, 8? I calculate the 1 and 8 first, and
the other permutations also, right? Yeah.
Yes,
so
that's the permutation.
So we have to do everything.
Yes.
That will be a big thing. Yeah.
Yes. Yeah. And then also for the BFS, we have the same situation. We have to permutate the whole array. Yeah, to get every output calculation output.
Okay. Yeah.
So here the time complexity will be constant only, right? Or because we have only finite operations?
Yes. The time complexity is constant because it only have 4 elements. Yeah, the permutation is 16.
How many operations do we actually do in this? can we
Mm.
total? Can you?
So actually, the operations will be huge. It will be something like 9,216 possibilities. That is what the upper bound it says in that
Yeah.
solution also. Yeah. So
How did they come up with that one?
because it is like if you have four numbers, right? So
Yeah,
four
four
number, the
number.
first two number, if you take it will be 12. 12 into other four, that will be 12 into 4. For the second combination, it will be 6 into 4. And the third combination, it will be 2 into 4. So if you multiply all of that, that is going to be 9,216 possibilities.
Use it. Yeah.
Yeah. Even the number is huge, but it's constant time complexity.
Yeah. But the so what are you saying of O of n? So the O of n is going to be time complexity 1, okay, and the space complexity also going to be the same.
Constant. Yeah. O of 1. Yeah.
Because we are just having 4 elements. That's all. Yeah.
So had the the time complexity depends on the number of operations or the length of the array. Like here we had only 4 operations. Oh, sorry, 6 operations. I think plus minus 1 2 3 4 5.
Yeah.
So if the number of operations increases and the length of the array is fixed, then in that case,
I think it should be the same, right?
Oh yeah, that is what is the confusion like.
Because
whether it depends on this. Yes. Yeah, go ahead.
Because the way she is doing, like 4 plus 1, so you can have n number of operations at each level.
Yeah, definitely, huh?
Yeah, so it is still going to be the same.
Okay.
That is what I think, yeah.
Yeah, okay. So it totally depends on the length of the array. Length of the list.
The list only has 4 elements.
It's only 4.
Yeah. It's not less than 4 or bigger than 4. It's just 4. Yeah.
Okay.
Yeah.
So you say like for I try to figure it out, still trying to figure out how to get that 9,000 operation. So you say like for two, right? And then 3 2s, and then 2 2s, is that? And then you add all the operation together to get the number?
Yeah, you just multiply them. You'll get the permutations, right?
Yeah, permutation. This. That means we choose 2 out of 4 to do the first calculation, and
4C2. It should be 4 choose 2. I think 4C2. 6 possible ways will be there for each. Every time you're selecting 2 elements out of 4.
It's
4C2 should be 6, I think.
6. 4C2 is 4 plus
6.
Okay, like 6. You have 6. Yeah.
Possible.
Yeah.
Out of which addition and subtraction are commutative only.
Yeah, we choose, and then we choose one of the operator. We just see it's a 4. 1 of 4 operate here. This is choose two number out of 6 number. And this 4 is operator. Choose 1 operator from the 4 operator. And then choose another one out of the 2.
So he's saying, like, the first one, when we choose 2 numbers, there will be 12 ways to choose the 2 numbers first. And then you perform 4 operations on them. So that will be 12 into 4. So when you reduce the least input from 4 to 3, so it will be, you are again picking up 2 of them, but at this time your size is only 3, and therefore it will be 6 ways to do that, and then you will again apply the 4 operations.
For
right?
operation.
So therefore 12 into 4 into 6 into 4, and then you will have the least input size of only 2 elements. So you have 2 and then have the 4 operations. So it will be 2 into 4. So first it will be 12 into 4, second will be 6 into 4, and third will be 2 into 4.
So it's
so even if we have n number of operations, it's just going to be the possibilities will be more, but still the O of time complexity is going to be constant.
yes. Now, anyone could just share the implementation?
I think you already have that, right? Why don't you?
Yeah. We can go through the approach. Yeah, but really, I'm not understand so well. Yeah.
Okay, so the first one, when you say that the double EPS, which stands for point zeros, actually it should be 0.00, 3 zeros and 1, you know.
0.
Yeah, so the reason why we take that value is, you know, if we have what is the least number what we can get from this? If we have all inputs as 9, all 4 of them as 9.
Oh, yeah.
1 by 9 is 3.
One of them. Yeah, 1 over 9. Yeah.
Yeah, 1 over all the 9.
Yeah.
So that comes to around, you know, something like 0.00015 or something like that. So you are slightly taking 0.001.
Okay, it's not too small enough.
No, 15 actually, 0.0015, something like that.
15, yeah.
Yeah.
Okay.
No, one more zero.
One more 0.
Yeah,
oh, really?
like that, yeah.
Oh, yeah.
So therefore,
Okay.
this one should be 0.001.
Yeah.
So yes, yeah. So that is the way. Okay,
Yes.
it might be the other way
Yeah.
there. So if you actually do the math, you will come to know. And therefore, this is the value. So whenever you do actually, and you're trying to, in your line number 10, when you are trying to return this, you are comparing it with the 24. And you try to see if the difference is not greater than this EPS value. Okay.
Yes.
Because you will always have an error 0. So that is what that EPS stands for, right? So there will always be a difference because it's a double number.
Yeah.
And you are trying to say if it is in that range, then you are considering that as a 24, or maybe it equals to 0.
Yeah, that's the termination condition for the DPS. Yeah. And we also have the operators and to do the DF. First, I have the termination condition. If I find the calculation, I always put the calculation result to the first element in the array. So if I found there is only one element in that array and the value of that element is very close to the 24, I think I found the solution and return true. And then I go through the numbers to pick 2 different elements because I are not equal J. So I find 2 different elements in the number array and calculate the operation result of that 2 element. Yes.
Can you explain line number 11? What is the relevance of it? I didn't get like nums of 0. Is the first element minus 24 less than epsilon value? I mean, EPS, whatever you have taken.
EPS is just a small number because I transform the integer to double. I need the real division instead of the integer division. So I transform the integer to double. So I cannot use the equal here. Yeah.
So it's kind of like a safety. Usually EPS, I guess we use it when we also divide, correct? Or
yeah,
that's for the division. Yeah, exactly. The floor division. So you'll always have an error in the range 0.001, something like that. So
Yeah.
Could you explain the for loop on line number 16? What is that
16.
for? 16.
16 here.
Yeah.
Yeah. 16 is put back.
So there she's actually doing the operations and then putting the rest of the elements inside it, right?
Yes, yes. Yeah, because I just deal with numbers. And so for the rest of the element, I just put them back to the number array. Because the next calculation, I need that unused element. Yeah, like this one, I choose the 4 and 1 here. So I calculate the 4 and 1 by using different operator, but I need to put back the 8 and 7 back to the array because the next step I'll use this 8 and 7. So that means I choose 2 elements to do the calculation and put the rest of the element back to the array.
Okay.
Yeah. And from 19, I just do the different operator. The operator array has 4 different operator, and I switch different operator and to calculate the t. The t is the calculation output.
Okay. So the operations you are doing it later, but you are actually including this number, the rest of the numbers in the 16th and 17th. Okay, before
Yes.
you do the operation.
Yeah.
Okay, yeah.
Yeah. Each time I just I always put the calculation output to be the index 0 element, and put everything back to the number array. And since it's a backtracking, so after I do the DFS, I popped out the T array.
So when num_j on line 21, num_j less than epsilon, EPS, then that value too small. So you consider it as 0 and then you ignore it?
Yes. Because I do the numbers, I divided by numbers j. In the division operation, I have to guarantee the numbers j is not 0. So if I say the number j is very small, it's close to 0, I just continue, didn't do that operation.
So it is almost equal to like an divide by 0 condition, right?
Yes, yeah. Okay. Yeah. Yeah. If you have another approach, yeah, you can share.
I think only the DFS makes sense here. I'm not sure whether there is another approach. Yeah, there might be.
Yes.
But the DFS makes more sense, and this is what you explained here. It is the DFS approach. You know, so I'm not sure if the DP works here.
DP might be.
Is there any overlap sub-solution in the tree?
In the tree, DFS tree?
Yeah.
Overlap?
I don't think so. It might be overlapping, right? Because you're going through each and every permutations. Because if there would have been overlaps, then we could have got 24 many places, right?
Yes.
So therefore, we get 24 only one place. I don't think we get it many places. Unless the number is something very 666. Yeah, but it's only the addition you will get, right? You're not going to get for anything. Yeah.
Yeah. If they're duplicate in the array, maybe we have the same calculation output in the tree.
Could you explain line 20 and line 21 again?
21.
20.
21. Yeah.
20 and 21.
Yeah. 2 lines. That's do the operation. If the operator is plus or the operator is times, and the I is larger than J, that means I didn't do any operation. Let me see. Plus I.
I'm not sure whether you need the line 20, but the 21 you surely need it.
Yeah, 21.
Yeah,
I
21
just
you need it.
Not.
And also in the
by error.
21 you need another, I would say, a condition saying if Ni is less than EPS, you know. And if you are actually, because if you are using I, dividing it by Ni, nums of I, you know, in that case also it might be something like, okay, oh yeah, I think what you're doing is you're doing the permutations on the top, so you don't need that. Yeah, I'm sorry.
Yeah. I just divided by nums J.
Only always you do it by nums J. Yeah, I got it.
Yeah. That's the line for line 20. I think maybe why I did the 20. For the array, I sorted first. That means it's an increasing array. And I and J is that means if I did the plus and times, I only need to do.
Oh, okay. Yeah, it only needs one operation. You don't want two operations for the same one. Yeah.
Yeah, it's
trying to optimize it. Yeah.
Yeah, it's a pruning. Yeah. Like one of the pruning. Yeah. Same question. I didn't realize it. Yeah.
No, that's okay. Yeah.
But why I greater than J and not J greater than I?
Because the outer loop for loop is I, and you can do the opposite way. It's just calculate half of it, not the whole calculation between these two number. Yeah, you can do it's a J less than I less than J, or J I greater than J. Yeah.
Yeah, because you are always using J as a greater number than I.
Yeah.
So you don't want these operations. But if you would have done the other way, then here you would have to reverse that condition. That is what you are trying to say.
Yeah.
So you only want to consider the indexes that are after the outer for loop. That's what it means.
It's the aim like you have two numbers, and A plus B equals B plus A. So I needed to do to do the calculation twice. I just one of them. Yeah. So it's not matter to I greater than J or less than J. I just keep one of them. Yeah.
So in this case, you do B plus A, and you ignore A plus B.
Yes. Yeah.
And you know, why you select the second one?
The second one, it's just randomly pick one half of it. Yeah.
Okay.
It doesn't matter which one you
not
pick.
On purpose.
Yeah.
Okay. I thought it's on purpose.
Yeah.
I'm trying to eliminate the other operation. Yeah. Okay.
Could you Could you explain the line 21? Because the conditions, they say they only contain a number from 1 to 9. So that means number j never less than EBS, right?
The numbers j maybe because the j is from 0 to the number of the size of the array. We put the calculation output to be the. I always put the output at the front of the num. So this output could be 0. Like we have the 4 minus 4, and this time we put the 0 to the nums I first element, and then we have the numbers I to be the 0, numbers j to be 0 now. Yeah, when the j is 0. Yeah, the full card is from the 1 to 9, but the numbers j could be the output of the calculation. Like if the calculation is 4 minus 4, the output is 0.
Oh, you put the output back into the number array?
Yeah. I put the output of two numbers calculation back to the number array.
Show me where you put that one.
Put in the front, in the beginning of the number array, like this.
Which line of code you put?
It's a recursive call, right? The helper function.
Yeah.
You see the nums operation here is the t.
This is t. Yeah.
Yes.
Yeah.
Oh yes.
Whatever
Yeah.
calculate, they go there.
One.
Yeah. Okay. Got it.
Yeah. Like this one, I put the 4 plus 1 to the 5. 5 is the first element of the array. Yeah. Let's avoid the denominator to be 0. Okay, any question?
No, I think it's clear. So.
Yeah, it's clear, thank you. It was a great explanation. Yeah.
Thank you.
Thank you.
Okay, Emily. Yeah, thank you.
Okay.
Is there a way to do the real calculation without using double?
Yeah, that will be slightly difficult because when it goes for the real division, then it might not work. Or else you'll have to keep something like a remainder and then the quotient and all that steps. You'll have to have some additional variables. So you'll have to have it for each and every one. So for at each and every level, it keeps on increasing. So that might be a lot of overhead.
No, I'm thinking like using the same algebra, like when we multiply, when we divide, we multiply the denominator over the numerator.
Yeah.
It can be. I'm not saying no, but yeah, it might add some more additional complexities. So.
Yes. Extra work.
Right. Yeah.
Is anything gonna change if we actually sort the array decreasing order?
I don't. Oh, okay. I think so. If you sort the array, it's not required to sort an array. That is what I was thinking.
By sorting the array, I just convert the int to the double.
Because you have to get each and every permutations of the number. So so whatever the way you do, you again have to do it. So.
Yeah, but usually when we go with the minus or division, we try to get the larger number.
Yeah. Sometimes it might help. Yeah, that's true. Some optimizations. Yeah.
Okay.
Yeah. Thank you very much. Yeah.
Okay. You'll have to stop the recording first. Yeah.
Yeah.